In this lesson we're going to look at similar triangles. Now two triangles are similar if one is a dilation of the other. And what that means is one is a magnification of the other. Now how do we prove that two triangles are similar? They may look the same, but if they have one of the following three, or meet one of the following three set of criteria, then they will be similar. Now the first one is that if all three corresponding sides are in the same ratio, and we call that side, side, side. Now what that means is if you had two triangles, which we can see here look to be quite similar, if we compare pairs of sides, say the left-hand sides, which are 2 and 4, we can see that to get from 2 to 4, or by taking 4 and dividing by 2, we can see that the second triangle, in terms of these sides at least, is double the other triangle. And if we look at the bottom side of the big one, which is 9, we can see that's double the corresponding side over here of 4.5, and likewise for 16.2, that's double 8.1. So generally what we do to find the ratio, or to compare these ratios, is to perhaps take the bigger one, or in this case the second triangle, and write down those ratios. So the ratio in this example is 2, and that was because we did 4 divided by 2 using the left-hand sides, and that turned out to be the same ratio as 9 divided by 4.5 and 16.2 divided by 8.1. So that's the first way. The second way is if you only have two corresponding sides known to be in the same ratio, but they have the same included angle, then that's enough proof to show that the two triangles are similar. So I'm actually using the same triangles as I had above. Now these sides here on the right are in the correct ratio of 2, but we don't know this. So the other proof that we need is that these angles between the two known sides are the same. So that 120 degrees there and that 120 degrees there is enough to show that these two triangles are similar. The third way is if all the angles are the same. Okay, there's no arguing about that. If you've got all your angles the same, the two triangles must be similar. Now, when you look at these two triangles here, at first glance, because they're in different positions, one's a rotation or a translation of the other, at first glance they don't appear to be similar. But when we actually examine the angles they contain, we can see that they all contain an angle of 85 degrees, they all both contain an angle of 45 degrees, and they both contain an angle of 55 degrees. In fact, if I took this triangle here and flipped it over and rotated it, I'd be able to overlap this one. So we've got to show one of those three things before we can start doing some maths on calculating side lengths. Let's do that now with an example. Let's find the value of x in this diagram. Well, okay, are there some similar triangles here? Well, yes, in fact there are. Looking at the big overall triangle, we see that it contains a right angle down in this corner. And this smaller triangle here also contains a right angle. Okay, well, we've shown that they have a pair of angles the same. But look at this angle here. In this corner here, this angle, whatever it is, belongs to the small triangle, but it also belongs to the big triangle. So we can show that there are two angles the same. And if two angles are the same, the third angles here must be the same. In fact, these are corresponding angles, you might remember from an earlier lesson. This angle here is in the same relative position as this angle here, where we have this line here and this line here as our parallel lines. Okay, well that enables us now to make a comparison, and the best way, I tell you, the best way to do this is to actually draw both triangles and then make a comparison. So looking at the overall big triangle up here, we write down its known side lengths. The right hand side here is 12. Now down the bottom, the distance from here to here is x plus 2. That's because over here the distance x that we're trying to find only spans from here to here. So with the 2 from here to here, overall this distance is x plus 2. If we just cut out this little triangle here, we notice that it's got a height of 5 and a base of 2, and we write that underneath. Now it's easy to pick up pairs of corresponding sides. This side of 12 corresponds to this side of 5, and this base of x plus 2 corresponds to this one here of 2. So we can now write these ratios down, because remember, for similar triangles corresponding sides are in the same ratio. So the base of the big one, which was x plus 2, is in the ratio to 2 as 12 is to 5. How do we solve a problem like this? Well, we could use our graphic calculator and just highlight this whole thing and use interactive advanced solve. That's one way. Or we can do it manually by cross multiplying. So remember that 5 times x plus 2 will be the same as 12 times 2. So we write down that. Expanding our brackets, we get 5x plus 10 equals 24. So now we can take this 10 to the right hand side of the equation. So 5x must be 24 minus 10. Remember that that plus 10 here must change its sign from positive to negative when it changes sides. Let's simplify that. 24 minus 10 is going to give us 14. So if 5x is 14, I can divide both sides by 5. Allows me to cancel those 5's, and x is 14/5 or 2 4/5. As a decimal, that would be 2.8.